That's just how it is. Alrighty, well, let's just go ahead and review. So we started with Maxwell, Boltzmann. And by the way, I'm lecturing off one set of notes, but I'm going to send you a second set of notes that's different than the one I'm lecturing from, and that's just for diversity's sake. It's more information, just heads up on that. Now, big picture, let me just stop here already at the beginning. If you think about what we did in this class, it's all about probability. It's all about how do I learn about things given that I only know its probability? How can I manipulate probabilistic information into other types of information? A case point being, let's write down the Boltzmann. Remember, this is the Boltzmann equation. Maxwell gets his name added when we talk about velocities. That's not a big deal, but just wanted to point that out. Remember, you look like an uneducated room if you get these details wrong. Okay, so there's this, and hopefully this isn't particularly mind-blowing at this point, but let me point out that, so all levels, so again, my handwriting has suddenly turned bad just recently. Okay, so whatever, here's the Boltzmann equation, and then we plug in things for energy and hilarity ensues, but again, let me point out some bigger picture things. I wasn't able to tell you about this at the beginning of class, but what you're seeing here is an expression which has energy levels. And we had energy levels for things like for vibration. You know, later when we did quantum mechanics, we learned that, I'm using the quantum number there, we learned about solving the Schrodinger equation and, God, what else have I got? H atom. Here I'm putting down the quantum number, minus 13.6 eV over n squared. So we have all these expressions for energy from quantum mechanics, and they're perfect. So what the hell is this really for, right? The answer is that this is a thermal average. What's happening is you have, in your job, since a lot of you are engineers, you're going to have a giant container, let's say it's full of gas, let's call that octane, and it's not at 0 degrees. If it's at 0 degrees, these are your answers, but in the ground state. The ground state properties from quantum mechanics tell you what's in that container if it's 0 degrees. Well, it ain't, probably. In fact, it may be even above room temperature. What this thing does, it tells you about populations or probabilities. Oh, wait, those are the same thing for thermally populating higher levels, right? So what this thing says, if you have some KBT, then you have some probability of not just being in the ground state, but some excited states too. What this allows you to do is look at this giant container and say, yes, most of my energies are in the ground state, but some of them are in the excited state too. And when I make measurements, I'm measuring an amalgam of all of those ones in the ground state, and those ones in the first excited state, and those ones in the second excited state. This allows you the mathematical toolkit to make to average all that smeared up properties into a result, which is what you would actually measure by your spectrometers or whatever equipment you have on there. So again, you can calculate expectation values from quantum mechanics and get this, which looks like this. But when you do it this way, it's a thermal average. Where this, in quantum mechanics, is state specific. Okay, so this gives you the energy of a ground state or an excited state. This allows all of them to be looked at to give you an average, which would be consistent with whatever your temperature is at. So anyway, okay, blah, blah, blah. I just thought, I can't really tell you so much about what this really is until we get to the end, which is kind of a shame. All right, so anyway, but what do we do with this? And I do have there's two Maxwell-Boltzmann questions. Neither of them are about velocity. They're both, one of them you've seen before. I do have previous questions on homework and tests. A couple previous questions have appeared in the final. It's not completely composed of that. I'm just trying to help you out, so heads up. Studying old tests is worth it. You're going to see some of the same questions, and then there's new questions. I have two Maxwell-Boltzmann. They're both, let me think. No, one's an old question, one's a new one. Just go ahead and tell you, I don't care. I want you all to pass. All right, now, when it came to Maxwell-Boltzmann, we plugged in 1/2 mv squared, right? Oh, now this is related to what's on the test. This is for energy, but when you plug in 1/2 mv squared for energy, it now tells you about velocity. But that's okay, because 1/2 mv squared is energy. It's both at the same time, right? That's kind of cool. So we end up with e to the minus 1, 2 kBt, 1/2 mv squared over the sum, e to the minus mv squared. Sorry, that's throwing me off. That's it's been a while since I've written this. Okay, so we started with this. This was like on our first day. We talked about what to do with this deal. It's the normalizer, and this guy you don't do much with. You also got to remember you're in x, y, and z, and what you end up with is m over 2 pi kBt. Now again, I don't have calculators on this, but we can look at this. Remember, m is in kilograms. Don't forget stuff like that. That may still come back to bite you in your professional careers. I have kBt at the bottom. That means I'm talking about a single molecule. If I had R, I'd be talking about a mole of molecules. It's not terribly important. 3/2, the 3 comes from the fact that we live in 3 dimensions. And again, this is the normalizer. Then we have this deal, e to the minus, the numerator doesn't change, kBt, but remember we're in 3 dimensions, and this, I'm talking about this because it was a bit of a sticky point on the last test. Again, remember on homework 11 that you didn't have to do, I posted the answer key, and I talk at length about 2 pages of notes on how to deal with this properly, but I'm going to cover it now because why wouldn't I? Okay, so what you end up doing is to convert this into, you need net velocity because net velocity is right there. To do that, you convert to spherical coordinates, and so you end up with a v squared sine. Now this is always correct. This will always be correct because this is the proper Jacobian and whatnot. And what I tell you in the problem set is that in quantum mechanics, you can always just do things with never mind. Let me just finish this up. Anyway. All right. Now, Maxwell-Boltzmann, the way you deal with this deal is different than quantum mechanics. I'll tell you that much. It's different than quantum mechanics because unlike quantum mechanics, there's no angles in the function. Quantum mechanics, there's angles in the function because there are wave functions. There are radial wave functions, there's theta wave functions, there's phi wave functions. And that means that that is different than what I'm doing here. Okay, now what I'm doing here is I'm going to just do 2 integrals. I'm going to do a phi integral, starts from 0 and goes to 2 pi. I got a theta integral. I may have written this out. I think I wrote that out incorrectly, didn't I? I should do it the other way. I label these because otherwise I get confused. And I'm not doing the radius, which of course is net velocity. I'm not doing that integral. I'm going to leave it alone. And what I end up with is 4 pi e squared. Okay, so, and then that gives us the correct Maxwell-Boltzmann distribution. You end up with the 4 pi b squared. Where am I at? So the Maxwell-Boltzmann as a function of velocity ends up being 4 pi b squared. Then the normalizer m over 2 pi kb t, 3/2, number of dimensions. And the question I have on the test, by the way, is I just make up something. I make up something silly. And silly is silly, but I did that just to see if you knew how to deal with this properly, which I'm about to show you. I just also want to point out that the way that Jacobian has a 4 pi for Maxwell-Boltzmann does not appear in quantum mechanical deals because the quantum mechanical deals, that 4 pi gets eaten by the radial wave functions, right? Maxwell-Boltzmann velocity doesn't have a radial wave function, so the 4 pi appears. In quantum mechanics, they have radial wave functions, so the 4 pi gets normalized out. It does not appear. So hopefully, I'm hoping you're following me, but regardless. Okay, so now what we do, of course, we want to, we want to integrate knowing the limits. So on the problem I ask on the test, which again is just another silly thing I just thought of, but whatever. Pay attention to the limits. And what's the answer? You should already know the answer. Yeah, it's 1.9. It's normalized. Which remember that in math, except for a couple of freaking examples in quantum mechanics, I can always take math expressions and put them in a way that a kindergarten would understand. Except for a couple of examples in quantum mechanics. That's why I hate that stuff. This says it is 100% true that a molecule is either not moving or is moving. Ta-da, right? So that's something a kindergartner would understand, right? So, but what good is that? Now here's the part that you gotta be careful of. Obviously, this is what I have on the exams to take the average value of something. So again, notice that. Right here, let me write this down. I'm going to write all values to make it a little bit more generic. But I've got this Maxwell-Boltzmann distribution. And so I'm multiplying it by the thing I want the average value of integrated over all values. And in the example above, and I'm going to rely on your, remembering some of what I'm doing right now. Remember, I took out all of the constants. I called them a Q. Don't forget that they're there. I do that so that it's a little bit more plain to see the form of the thing the form of the function I'm trying to integrate, and you do that to match it to an identity on the cheat sheet, because you don't have to do any calc in this class at all, although that's incredibly weird. And actually, I think I remember the answer, but whatever. Right, at this point, you just don't forget the constants, copy this off the cheat sheet. Even if you just did that, I'd only take 1 point off that, then write it all out, and then you get full credit. You don't have to simplify as normal. Remember that you can calculate the average of v squared, and that means you just square it. So the thing is that you have anything you want to figure out with this, you can, as long as it has velocity in it. And you probably want to calculate something that has meaning. When I do average velocity, what's cool is you see that molecules move faster than the speed of sound. It's just that there's some intrinsically interesting human things that we can know about the air in front of us. And I'm still shocked to this day that on average, most gas molecules move faster than the speed of sound. It's very counterintuitive to me, but now I know that. Wow, that's kind of cool. Now if I do this, then what I can do is calculate 1/2 m average v squared, and I get 3/2 kBt. Remember, this is actually proof of the equipartition theorem. This is a perfect gas because we never included any interaction in the energy. It's just pure kinetic energy, so the gases aren't interacting, so this is a perfect gas. And you should have 1/2 kBt for every degree of freedom. We learned that last semester. There's 3 degrees of freedom because we live in 3 dimensions, and it gives me 3/2 kBt. I just proved the equipartition theorem from last semester. Kind of cool. So, and I also want to point out that what this is really like is if you want the average value of something, really, the other way that you've seen this a couple times, and I know this threw you off too, is that what you're doing is taking that something and multiplying it by the probability of that something. I know that's horribly funky, but average energy of harmonic oscillator. Sure, that one's easier. That would be the energy of the harmonic oscillator times the probability of the harmonic, that it has that energy. energy times probability. This, when the energy levels are very close together, turns into an integral. So sums. This is the way this is nature's result. It turns into an integral when you have things like velocity, which are not really occurring in steps, or not. It's not so easy to observe that they occur in steps, and yada yada yada. So. Oh God, what else do I remember? We did relative velocity. I didn't put that on the test. I'll just tell you. Whatever. Minutia. I didn't put too much minutia on this test. One or two, but I didn't include that. But
what's the one or two?
What's that?
What's the one or two?
Oh well, what are my cat's names? I thought about putting that on there, but that's too much. I was tempted.
Charlie and...
Yeah, I was about to say.
You like Charlie.
Charlie's okay. Charlie's the one that throws up all the time. Zoe's my girl. She's my wife. I was about to say, I'm about to change this test, and not in a good way. If you don't know those cats' names at this point. Let's see here. Okay. So I spent a little bit too long on that, but I just wanted to give you a really big picture. And you notice how I've been including Maxwell-Boltzmann. I've been trying to re-inject that into the last sets of problems because, for one, I wanted you to remember it because it's one of the hard questions is an average value. It's like goat power per internal energy. So it's made up. It's silly, I know, but it shows me that you can. I don't want you coming in here memorizing stuff, right? And that makes me comfortable that you're not doing that. And so it's an average value question. And but I want you to get the big picture. Quantum gives you energy levels for states, and that's great. But thermal energy makes things occupy multiple states. And when you observe them, you're observing an amalgamation of those. So that's where they kind of blend together. Maybe I would do Maxwell-Boltzmann second and quantum first. Anyway, okay, black body radiation. So I know it's a lot of minutia here. And I'm thinking about next semester, I'm actually doing this class again for PChem 2 for biochemists. I'm thinking about doing it differently, where I actually cover the material in reverse. So here's the intensity as a function of wavelength. And we all know that, well, it's minutia, but if a lamp is about 5,000 degrees, that's the same temperature as the surface of the sun. So that's a nice white light bulb. It makes us happy to have light that works at those wavelengths. Fluorescent light bulbs do not look like this, and it makes us depressed to be around them. So when I have a light bulb at 5,000 degrees, it looks like the sun, and it tends to literally brighten your mood. What I did that I'm going to try to do differently is I ended with this drop-off. And this occurs because of Boltzmann. Okay, so what's happening is this light bulb has temperature and it's producing light. Now it can't just keep producing shorter and shorter wavelengths, which are higher and higher energy, because it becomes improbable because of Boltzmann factor. So already I should be talking about thermal averages because I'm talking about something that's hot. It doesn't actually matter, it doesn't have to be hot, but anyway, so the Boltzmann distribution goes as E to the minus NHC over lambda kBT. Hc over lambda is the energy of a photon. And remember the part that's funky about this, and some of you choked on this, is that the light bulb is allowed to have multiple photons to make the Boltzmann distribution work. So for a given wavelength, it has multiple photons at that wavelength. And so anyway, so again, I'm kind of doing this a little bit backward than I did last time. And we talked about solving this and yada, yada, yada. Okay, where it got a little bit more interesting And this is why I think I should probably next time start with this and explain the drop-off, but then now I want to explain the rise in the emission spectrum of a light bulb or the sun or anything that's hot. And that has to do with Ampere's law. It's actually like a corollary of Ampere's law, something like that. And you also, remember I was telling you at the time that I wanted to cover this because this is very quantum mechanical-like. And now, in case you forgot this, you're looking at this and thinking I'm writing a Hamiltonian. I'm not, I'm writing Ampere's law, or corollary, whatever the hell it is. And of course, what you do is I'm writing this in a very mathematical form, as though we're in a math class. And that's because I didn't give you the function. The function, of course, that is applied, you apply the electric field, which is a function of x, y, z, and time. So right, now recall this really does look a lot like quantum mechanics. In fact, for those of you who attended one or watched the video of one of my extra Friday hour lectures after, I think, the second test or third or first test when there was a little bit extra time, I showed you the time-dependent Schrodinger equation. This is almost identical to the time-dependent Schrodinger equation. So again, this was a nice warm-up. Now what you get from this is, I mentioned how, maybe I should follow my own notes, that you have a light bulb. Here, I'll actually draw a light bulb. Maybe I should do it this way too. You have a light bulb, right? So I'll draw it very light bulb-like so that you know what I'm doing. Okay, so that looks kind of like a light bulb. What you've got to do is you've got to make the waves, the light waves, fit in the light bulb. And that is, now I don't quite get this, technically this counts, this is half a wave. I never got this, it's half a wave, but apparently it counts. I don't get that. The next wave that fits looks like this. And these are by the way, these are particles in a box. The exact same thing. Yada, yada, yada. And so this ends up being sine. We have a little thing for nodes. I've got a length of the box, which is actually the size of the light bulb, and yada, yada, yada. So anyway, also the functions multiply. Here, I'm just going to leave it like that. Y and Z, again, I'm just reviewing, hopefully you remember this. Okay, now what you got out of this, knowing that there are only certain waves that fit in the box, we can start plotting the allowed number of, the allowed wavelengths. And it looks something like this. Now, as we got to shorter and shorter waves, the number got higher and higher. So I'm trying to represent that by increasing the density of states. And this is something that becomes very important in grad school, and I can't continue doing what I'm doing, so I'm just going to represent it that way. So every one of these lines represents a wavelength which is fittable in the box. Now, the intensity is the number of waves. Now, that was something that, this was probably, I don't know, I hope it didn't shoot over your head. It kind of shoots over my head. But we talked about how as you have more and more nodes, you had this thing that keeps track of the total number of nodes. So notice that I'm talking about nodes here, and how that this grew like a sphere. And so basically for any given wavelength, there's multiple NX's and NY's and NZ's that correspond to those wavelengths. And as you get shorter in your wavelength, there's more of them. And that's why the number of waves increase. I know that's a mouthful again. For any given wavelength, wavelengths are determined by the number of nodes. As you get shorter and shorter, and as the number of nodes gets higher and higher, you actually have more combinations of NX and NY and NZ that give the same number, the same N squared. And that means, that's why I'm drawing these at higher intensity, again, as I get to shorter and shorter wavelengths. that's multiplied by the Boltzmann equation that then kills it off. Yeah, so there you go. That's the whole big picture of this. The other important thing was you were able to do Maxwell-Boltzmann in terms of sums, so I wanted you to see that as well. You also saw that energy, don't write this down, this isn't important, energy of light was hc over lambda. At one point they thought that light was the same as a gas. They thought that every photon had 1/2 RT of, 1/2 kBT energy per degrees of freedom, there being 2 degrees of freedom because light is right and left circularly polarized. Remember that Einstein showed that light has momentum h over lambda. That was just kind of cool, explained the photoelectric effect. So at the time when all of this was being discovered, people are realizing that light does not behave like a lot of things should classically. It does not behave like busy bees in a gas. Remember, I'm always talking about for last semester, gases like little bees in a little balloon or something. And especially when we got to this allowed Schrodinger, Heisenberg beat Schrodinger, and de Broglie to start developing quantum mechanics. De Broglie started off the whole shebang. Here, I'm not using my notes, by the way, and you know that's bad. Okay, so, this guy Heisenberg, remember him from the Heisenberg uncertainty principle, which was a real pain. Heisenberg actually came up with the Schrodinger equation before Schrodinger. Just a cool story. He expressed it in a mathematical construct that no one could understand. Schrodinger comes along, I don't think he cheated, he figured it out just at the same time, and he put it in the way that we do in class, and it was easier for people to understand, so we got all the credit. Okay, so the Schrodinger equation development. So some minutiae here for you. Let's see. Okay, now these guys were all physicists. Physicists don't like to do kinetic energy with 1/2 mv squared. They like m squared over 2m. They always like to put it this way. Chemists, we tend to teach you 1/2 mv squared, but they do it this way. It's the same thing. Just a matter of just pick one. And they pick this one. And we develop quantum mechanics, so we use this. Now, let's also forget potential energy, because let's start simple. P squared over 2m. Okay, fine. What else we got? De Broglie, by the way, he looked at Einstein's theory of relativity, which gave us light having momentum as though it has mass, even though it doesn't, which is weird. And he said, well, mass doesn't have a wavelength unless, wait, am I doing this wrong? Yes, I'm doing this wrong. Sorry. If light can have momentum when it has no mass, then mass can have wavelength even when it's not a wave. But not. And so he wrote this down. Now, I'm sure that his thesis, which he's the youngest Nobel Prize winner in history, he said this, and apparently his thesis committee didn't believe it, didn't understand it, so they had to send it to Einstein, who said, yeah, this seems legit. So I'm sure he didn't just rearrange Einstein's equation and say, well, there you go, good luck with that. But this is the idea. And so matter has wave-like properties. And I see, so we got momentum here and I got momentum here. So Schrodinger is trying to bridge the gap. And it has wave-like properties. So he's trying to make matter work like a wave with this wavelength. That's the idea. And he's trying to get something he can measure like kinetic energy. So he's got to get all these together. Remember how I was telling you when we started quantum? I think you see it now. When I cover quantum, there's like 5 things you have to know simultaneously, but I can only cover each one at a time. This is why it's so awesome. But hopefully it's all clear now. Okay, so if you're going to be a wave, let's model you, whatever you are, maybe it's just a particle in free space, with this. Okay, that looks fine. I know that when a wave goes from 0 to its wavelength, that I've done a full wave. So cosine should go from 0 to 2 pi. this junior year trigonometry, anyone, right? So junior year trigonometry, you know this. All right, so, okay, I got this, all right, hold on, let's see here. Now we're coming, I gotta look at my notes. So now I got, what I want to do is call this cosine kx, where k is 2 pi over lambda. And so I've got my wavelength in here, and I've got, let's see, therefore, p is h over lambda, so this is 2 pi over lambda. So k and p really ought to be the same thing, just offset by an h constant, or an h bar constant, which is 2 pi. So again, k is 1 over lambda, p is 1 over lambda. So I've got my momentum, so now I need to put that in here, and I'm set. So now how do I do that? Okay, so here, let me just erase real quick. I'm still not writing the operator yet, still just trying to slow walk you through it. Given that I believe you already understand this, so I hope this is a little bit better. Okay, so therefore, p squared over 2m, and now let's put in the de Broglie relationship. So p squared is h squared over lambda squared, and this is going to be h bar squared k squared over 2m, given, of course, that h bar is h over 2 pi. And let's see, does that make sense? If I plug in, if I plug in 2 pi squared over lambda squared, 2 pi squared over lambda squared, then I would have, then I'd have 2 pi squared on top, and there's a 2 pi squared on bottom. So yeah, I'm set. Question? Okay. Oh, I saw a hand raised. Anyway. Okay, so this is cool. Last trick. Now there's two things to this.
Where does the 2 pi come from in the top equation?
What do you mean?
So in the middle part where it's 1 over 2m h squared over lambda squared?
Yeah.
Correct. Where does the 2 pi on the h bar come from?
No, you added, you hold on. It's the same thing. Okay, so let me plug in the definition of h bar. You've added it in, you've multiplied and divided it out. So h bar squared is h squared over 2 pi squared. K squared is 2 pi squared over lambda squared. 1 over 2m is 1 over 2m. And so look what I've got. I've got h squared over lambda squared, 1 over 2 pi, 1 over 2m, which is p squared over 2m. Right? So multiplying and dividing by the same numbers. Craziest, simplest math trick in the world that simplifies everything. And you know, h bar always appears in everything. It's just to absorb it. It's just so that we don't write 2 pi in every freaking equation. He just absorbed it into h and it always takes care of it. And that's because ultimately that comes down to humans love frequency, but nature doesn't do frequency. Nature does angular frequency. That's how nature sees it. We see it as frequency, nature sees angular frequency. So we have to do this to kind of go from what we humans like to measure and the way we think to the way nature thinks. There's a little bit of a foo bar there. Okay, so we've got our wave functions, masses, we've got de Broglie. All you got to do is get this to give you this, right? So I see a k, so I know I can get the k out, but I'm missing h bar squared over 2m. I'm missing that, so there you go. I'm just going to multiply it. I mean, h is a constant anyway. Mass is a given. I know if it speeds up that the mass can increase, so let's not worry so much about that. I think some of you guys kind of a little obsessed with that. And again, to get k out, to get k squared out, I simply would take the double derivative of the wave function. And look at that, I've got a k squared out. Problem, there really is no wave every equation we have for a wave, if you do a double derivative of it, you're going to pick up a minus sign. So Schrodinger just said, oh, I know how to take care of that. I'll just add a minus sign. Cheap, but effective, so that's fine. So there you go. That's the Schrodinger equation. That's how it all came out. And is there anything else I wanted? It seems like there's something else. Oh, okay. That's also I want to say. Okay, and then this ends up being kinetic energy. And of course, later on, we added potentials and whatnot. But there you go. If you can't do this, you can't do anything. That was his thinking at the time, too. Now, there's another reason behind this. I did mention this at the time. It's not on the test, but I just want to point out that this is the equation for a string. This is the equation of musical instruments. I know it makes you go, ooh, that's tingly now. Quantum mechanics uses the same mathematics as musical instruments, and that's true, and there's no other way to explain that. I just think that's kind of neat. That's another reason that Schrodinger thought that it had to work this way. Eigenvalue equations, standing waves, they're musical instruments. It's all the same thing. It's all the same equation. So that's another thing that another reason for him to set it up this way, use eigenvalue equations, because it describes musical instruments. Okay, now, multiple dimensions. What do you do with that? That was quite easy. You just simply add them. I'll just do to y. Notice that I didn't go to z till the end, just because I didn't want to needlessly complicate things. The wave function, of course, is then a multiple. Right, you take an x and a y, they're the same thing, and you multiply them together. Do not add them together. You had a homework question where you found if you added the wave functions, you can't make eigenvalue equations work, so that's just not right. When you multiply them, you can apply these operators and you get it to work right, and that just means you get an eigenvalue equation to work right. Okay, so what else have we got? Let me just go over about 5 minutes because I see I'm actually a little bit behind. However, I get a little bit more comfortable. The closer I go forward in time, the closer it is I'm counting on you hopefully remembering some of this stuff, because I bet some of this has been like, oh yeah, I kind of remember that. Oh, and also I warned you that the test is very descriptive, much more like test 3. What is quantum mechanics? No, not that question, but one like it. You're going to laugh when you see it. That's about half of it, very descriptive. Let's see, what do I want to... Okay, so once we had... I had you looking at k, cosine kx, not that that's particularly hard. The kinetic energy operator. In the kinetic energy operator, no matter what problem we worked on free waves, particle in a box, multi-dimensional particle in a box. I spent like 10 minutes on it because it's as simple as that thing. As simple as that. There's nothing to it. Then we had, vibration. Oh God, then we went to rotation. No matter what of the example problems we can have, and if you do more advanced stuff, it's always the kinetic energy operator that's the biz knocker. It's the one thing that always makes this way freaking hard, because it turns this into a second order differential equation. All right, so what? All right, so anyway, so we covered kinetic energy. That guy, Caleb. All right. So what are the so once I got you thinking about waves and the kinetic energy operator, and again, that is the thing that kind of just makes everything work the way it works. Eigenvalues. So I did not ask you what is an eigenvalue equation. I did that on the second test. I did not put that on there, but anyway. So everything's got to work this way. Oh, I did have, I'll just go ahead and tell you. I have an eigenvalue equation for the last question, the extra credit, the 5-point extra credit. I have a radial wave function and a radial operator, and just have you show it works. It's kind of hard, okay? It's like 5 or 6 steps. And I did that because you folks did really well with, I threw a radial. angular. On the last test, I threw an angular operator, and you all nailed it. And so I put that on for the last question 13 extra credit question. A hard one though, so be careful there. Do it last. Okay, everything's got to go this way. Also, now this is a big one. Right? So that means that wave function squared. Wave function squares are probability densities. Okay, so if your wave function is a, let's just draw a let's just draw a wave function. It's just, my cat drew that. Okay, so that's what the cat drew. This doesn't mean much. Wave functions by themselves never do much. No matter how you operate on them or God knows what, you ultimately are going to find that in some weird way they're always squared. They always get squared somehow. Maybe there's an operator between them. You know that, of course, this means this because we have so many complex, and you know I can't draw a star still. There we go. Still cannot draw a star. Anyway, because we often run into complex deals, this is true. And so, yes, I see it now. Thanks. This should be therefore. Therefore, what this, and I should label my axes. That's something you learn in grad school. So now what I see is, where is the particle? Right now I can interpret this. This I can't interpret anything from. It's useful, but only to give me this. Now I see that I will probably find the particle here, and maybe here, maybe a little bit less likely based on the way I drew it. I will not find it right there. I don't know why that is, but whatever. But that's what I know. Now with this, I told you at the time, I gave you something. I was trying to make you comfortable before I showed you the real horror show, that you can then try to do things like this. That once we covered a lot of this quantum stuff, and this, and complex normalization, probability distributions, I had a feeling like at this point you're like, oh, all these 5 things I told you, you have to know 5 things at once to understand it all. Like 5 things at once. I have to show you them in order, but you need to know all of them for any one of them to make sense. It's very frustrating, but hopefully I haven't screwed up too badly and you kind of get it. And now I'm lost in my notes. Anyway, so to increase your comfort, I tried to do this at the time. I tried to do this to point out that you actually have a similar situation as Maxwell-Boltzmann. That you can take the probability distribution and multiply it by the thing you want the average of, and let's go ahead and put like all limits. Of course, that would always work. Probability distribution times the thing you want the average of gives you the average of that thing. And so there you go, right? So I showed you that to be like, hey, look, we're back at Maxwell-Boltzmann. It all works the same. You just got to remember to square your wave function. And just like, what was it, problem set 8, where I tried to make sure that you didn't screw this up, Maxwell-Boltzmann, swear to God, do not square a Maxwell-Boltzmann distribution. If you have a wave function, square the wave function. Don't square a Maxwell-Boltzmann. That is where everybody messes up every freaking final I've ever given. So anyway, you know that. Now, also, I showed you this, but you know this. This is a special case. X is a special case. The real equation is this. You know that it's this, right? Psi star. If it is complex, if it's not, then it doesn't matter. That's the real equation. It's just that X can, what is that? The commutative property of multiplication. You can move it around. Anyway, you know that if you're doing this, then you got yourself a bit of a problem. I can, that is one where you've got, oh, hi. Where are you? There you are. Hi, H-bar. Okay, you know that if you've got, let me put it this way. You know that when you get more complex more complex operators, then it doesn't quite look like a Maxwell-Boltzmann. I showed you X because I can turn that into a Maxwell-Boltzmann looking thing, but I can't do that with other operators when we have derivatives into them. So that's why I wanted to show you average value of X, and I knew that later we would do these harder ones. Okay, well, we do need a break. Let's see, I just quickly wrote up here, I just wanted to remind you, you don't have to write this down, I just wanted to remind you that once we had set up quantum, we ran through a gamut. This is very traditional, despite all my wonkiness and talking about cats and whatnot. I do want you to see the traditional pedagogy of quantum mechanics, because in case I have no idea what's on an MCAT or whatever professional development is expected of you. So I always cover the things that are, prototypical of this class. So free waves, particle in box, yada, yada, yada. So we started with free waves. We spent really a heck of a long time on it. And just to remind you that we started with the wave functions, pure kinetic energy, because again, if we can't handle a no potential energy deal, then what the heck? Then there's really no hope of doing these more complex ones, right? So we started with particle in a box, and we started writing down wave functions, and those are great because they're eigenvalues. And right and left, we looked at momentum. Momentum is positive, momentum is negative, so one's right, one's left. It's very straightforward. And then there's one thing that was kind of interesting, was that we were able to do things, like cosine. We were able to do things like this. And this brings up, now remember the normalizations of these things. I appreciate the fact that free wave problems are easy to understand. The negative is that their normalization is technically 1 over infinity. Technically 1 over the square root of infinity, which is unrealistic. The whole thing is actually terribly unrealistic, but it's a very good way to start. Okay, right, left, and then we can add these together. Now, the funky thing is that sine and cosine are not eigenvalue equations, which is how we, the thing, I don't know that I explained this very well. I was kind of a little teased with myself because I don't know that I explained it very well. But when it comes to eigenvalue equations, right, I showed you how this does not happen. When we were doing free waves, and we talked about how when we had wave functions of sine and cosine, the eigenvalue equation will fail. And I told you if that happens, then the number you get is invalid. So obviously cosine turns into sine. And so that means that this is no, that's meaningless. Whatever that number is, it's invalid, throw it out. However, what you can do is this. You can do this and the result is fine. It's okay if you do it that way. It's a very strange thing. But the reason that works is because cosine can be decomposed into eigenfunctions. Right? Now, I don't know if you recall this. It was a while ago, and it was a bit of an intellectual mouthful. But this fails, but this is okay. This is why we often express things in terms of average value. The reason it works is as much as this guy is not valid, it can be decomposed into functions that are eigenfunctions, that are valid. And the end result is actually is actually correct, in which case you get 0. Now, the other thing I wanted to mention about free waves, again, there's not much to talk about when it comes to these two guys. There's no quantum, you don't see energy levels because there's no barriers, there's no boundary conditions, the things that give you barriers. And that just means that any K is okay. That means that any energy is okay. That's how we interpret that. Again, all really straightforward. So straightforward, I didn't even put that on the test. This guy gets interesting. This is where you start to see the Schrodinger's cat problem. The popular literature, people on websites and YouTube are going to tell you that if the wave function is a cosine, the particle is moving right and left simultaneously. The cat is both alive and dead at the same time. That is false. That is a misinterpretation. And I don't mean it's like I don't feel that that's the answer. It's not the answer. This particle is not simultaneously moving left. It is not simultaneously moving right. That's ridiculous. The cat is not alive and dead at the same time. That's ridiculous. The answer is you don't know whether it's moving left or right. You don't know whether the cat's alive or dead. With that lack of knowledge, you have to incorporate that into your description and your model. This doesn't say it's moving left and right at the same time. It says you don't know which one it is. And this is the proper model for that situation. And anyway, so that's just, as college-educated students in STEM disciplines, you should know that when you hear that, it's BS. In fact, when you get to a PhD, and I hope you do, you will be horrified by what you see in newspapers, because it's always completely wrong. So anyway, let's see, so there's this stuff, and then, oh God, then we had barriers. Let's see, I wanted to talk a little bit about, okay, free waves. When it came to barriers, and I am thinking of a barrier question right now, by the way. So there's a step. Remember that the wave functions are always, we have one in region 1. I tended to use Roman numerals. We have another one in region 2. And so we make the x-axis something convenient. Okay, and there's a potential step. The wave functions are always basically a e to the I kx plus b e to the minus I kx. Okay, and then what you had to do is, depending on the nature of the potential surface, you always had to make the boundary condition work. And that is always continuous. This is continuous. And then there was smooth, which is the derivatives have to be equal. Now, not only the derivatives have to be equal, but it's at the point where there's the barrier or the whatever, the wall. I'll do wall is the particle in a box example. Anyway, okay, so you have continuous and smooth. So once you have a free wave and you start messing with it, then things start to happen. So now I'm introducing potential energy. Now, in this case, you still did not have a perturbation so strong that you got quantum energy levels. The energy levels are still continuous. There's no quantum in quantum mechanics yet. Because again, I haven't perturbed it with boundary conditions to the point where quantum energy levels have come up. It's still continuous. But you did see some neat things. We saw that if energy of the particle was started out a little too low, that of course it couldn't penetrate the barrier, but it actually could to some degree. And here's a wave with a very long wavelength, which means that there's very little kinetic energy. Okay, so again, the interesting thing is that even though it doesn't have much energy, it still gets slightly into the barrier, but it still reflects 100%. If it does have more energy, and of course you know, I was always kind of thought this was very important. So it's wavier. If it does have enough energy to penetrate, the amplitude drops and the frequency also drops, i.e. wavelength gets longer. Frequency becomes less, wavelength gets greater. Amplitude drops. I tried to draw that. Maybe didn't do such a good job. So anyway. Okay, so again, I am thinking of trying to put one of these questions in the final. This is the last question I haven't written yet. I'm just trying to come up with something new. It's something easy, and if I fail, I won't be able to do that. But anyway, I'm working on it. I will make it easy, of course. And there you go. And so work on the problems that you've seen before, and those will be easier than the one I asked. I'm a little struggling on that one, though. Just heads up. I just wanted to let you know that. Why wouldn't I? Okay. There was other things like finite barriers, and I had a handout that's like 20 pages long. The finite barriers are a nightmare. Trust me, that was an awful 2 days it took me to write that. But I wanted you to have that just in case you were curious. Then what got much more interesting was particle in a box. And that is when our potential energy surface finally gained a level of complexity that interesting things started happening. Now remember, I can center the box at 0, or I can center the box at L over 2. I like to center the box at L over 2 because the wave functions are much easier. They're just sine functions. There's sine x, there's sine pi x is sine 2 pi x. I don't actually know what it is, whatever. Anyway, so, oh hell, what am I doing here? So let me normalize it. 2 over L sine pi x over L. You can also see that momentum is pi over L, right? That's the K. You know, the K is what's in front of the X. Pi over L is the momentum, and K squared over 2m is the energy. So when I look at this one, and oddly the normalizations are always the same. I don't know that there's any physical meaning or any insight into that. It just is. Maybe there is some kind of physical insight that the normalizations are the same, and I don't know it, but whatever. So what you're seeing now is for the waves to fit, now that I've perturbed the free wave really freaking badly with these walls that are infinite, now that I've given it a real hard boundary condition, now I'm seeing quantum energy levels, discrete energy levels. Now they show up. And then I can start doing things like put them into the Boltzmann equation. And there's a homework question on that, and there's another one I think on number 11. And I'm also seeing that the energies are occurring in finite steps. K squared, h bar squared over 2m, which is still the kinetic energy. There's technically no potential energy because the wave function doesn't leak out the side. What is this? So k squared is pi squared over L squared, h bar squared over 2m. And let's look at this one. K squared, h bar squared over 2m is 4 pi squared. So look at that, it's much higher energy. And you know that I often harped on, like, what's your interpretation of this? I didn't put that on the test because at this point, you know that. This is the ground state, this is your excited states. You learn about those in freshman chemistry, hopefully in high school, that things have ground states, things have excited states. And they're finite, and so there you go. That's where you get all this stuff from. And remember that there's actual models for these. Now, what I was able to do with this, though, was then introduce the uncertainty. The Heisenberg finally gets his name in something. They had to give Heisenberg something, because the guy really came up with quantum mechanics. So I'm not going to write Heisenberg because I don't know how to spell it. But the uncertainty principle, think about it, that's L-E-R-A-L. Anyway, uncertainty principle, which is that the uncertainty in, let's say, an X operator, any operators versus another operator, remember that a sigma is technically, oh, I have to think about this. Technically, it's this. Now, this is a standard statistics formula. By the way, this is not a quantum mechanics thing. College graduates, you should know this, okay? If not, I didn't need it on the test. Okay, the multiple of two operators that have an uncertainty principle, and we talked about how you know that. It's when the operators don't commute. I don't think I put that on the test because I find that to be kind of a pain. Okay, so the commutator of whatever two operators, and that's just the difference of xt minus px. And again, we've beaten that to death. And so you can't know where something is and how fast it's going. The more your certainty in position increases, your uncertainty and momentum increases. So if you know where it is, you can't know where it's going. And this, again, is something you hear in the popular literature. So now you have a little bit more of a mathematical foundation for this, and you work this pretty hard on a homework question. And so look at that, or not, whatever. What I really like much more is to draw I'm actually drawing a state particle in a box. Let me draw a narrow one. This is not really a valid wave function for a particle in a box. I'm drawing a thin bell-shaped curve. It's not one of the eigenfunctions. What it is I could create this from summing a bunch. I could sum a bunch of these and equal this. I could do that. Or I could sum this I could sum a bunch of e to the I, k, x's. I could sum a bunch of free waves and get this. And it would be a bunch. This would be a bunch. And that's because it's so narrow. And that also, you also had homework where you saw that if you have to add more waves have more energy. Where do you think I get the waves from? If I have to add more waves, the waves have to be wavier. I can't de-wave them, I can increase the waviness, I cannot decrease the waviness. I only have a limit to how much I can decrease, I have no limit to increasing the waviness. So when I have a large number of waves necessary, it necessarily at the same time then has higher energy. Remember, these waves have kinetic energy. The more I add, and because they necessarily have increasing kinetic energy, it has to be higher in energy than this guy, which, okay, that's more like the ground state. I drew it a little bit more like the ground state. This guy is composed, again, of the same, still of a sum of these kinetic energy waves, but few. And again, there was a handout on that, and I'm going to label axes. For those of you going to grad school, label your axes. It's a big mistake not to do that anyway. So this is a manifestation of the uncertainty principle, by the way. It's hard to see the connection between this and this, but let me try to walk you through it. I know where this is. This is small, therefore that's big, because this is a constant. Okay, if this is big, you have to have more waves, and I've already told you why that's higher energy. So you can kind of see how these all flow together. It's a bit of an intellectual mouthful, but this guy, I'm not sure where it is, so that means I have more certainty in momentum, requiring fewer waves to make an accurate description, and therefore necessitating less energy. Again, I had you work some numbers on a little table on one of your homeworks to show you that. So, what else do I want to say? Yeah, I guess I didn't have much else other than we then talked very briefly about multi-dimensions. And so then we did a little bit about multi-dimensions, something that, you know, every time I teach this class, we're on the cusp of graduate level. And when you get to graduate school, instructors will sometimes really develop blah, because I mean, this stuff is, I've been doing this years, I'm twice as old as all of you, and I've been doing this the whole time you've been alive. It's still freaking hard. It doesn't matter how long you've done this, hard is hard. And so, when you get to graduate level, your instructors will definitely flub up plenty of time, no matter how old they are. And I often find new things that are interesting, and I tend to emphasize those every time I teach the class. When it came last semester, and maybe some of you who watched last semester videos, I was obsessed with degeneracies. Not so much in this class, I don't have this on the test. But when you do multi-dimensional and you write out the wave functions correctly, you find that the energy ends up being nx over, let's say that the box lengths are different. The point of this is that then you have degeneracies. Only when you have multiple dimensions are you allowed to have degeneracies at that point. So another little factoid about this. All right, the next thing we did was vibration. So that's on the list. Let's see. Now there wasn't much about that because this is the point where, excuse me, I stopped trying to do so much proving. Once we had, this was when we finally had a fairly decent potential energy surface. 1/2, I think I called it KF x squared, I call this x. Now remember, it's centered at 0, and that actually would represent an equilibrium bond length. So if you this is technically expanding the bond, which of course increases the potential energy. It's a spring, and we can contract the bond, and that's moving to the left of 0. Remember that the reason we did that is it just simplified. It just simplified all the stuff, essentially. I also, at this point, stopped trying to prove the Schrodinger equation. I just said, here's the Hamiltonian and here's the wave functions, and wave functions gives us energies and yada, yada, yada. Go to grad school, that is where, when I was in grad school, that you see the differential equation solved. Takes like an entire week, but it's grad school. You're paid to go, that's cool. So anyway, so we have now a legitimate functional potential energy surface. Of course, we did see quantized energy levels. We're always going to see quantized energy levels once we get past the free wave, once we get past the silly, stupid barriers, simple barriers. Notice that always the average value was 0. That's just kind of a neat little factoid. Let's draw, you know, the wave functions really look like particle in the box. They're very close to particle in the box. Oh, I didn't draw that right. I messed that up. Oh, I messed that up hideously. Now I'm perturbed. I got to do this right. There we go. Oh, God, I screwed that up. Anyway, I just thought it was kind of neat that even when you're doing excited states, let me see if I can do this. Now I'm bothered. Anyway, there we go. Even when there's a node in the middle, it's symmetric left and right, so it integrates out to an average value of 0. So everything's always at an equilibrium bond rate. I thought that was kind of neat. And there wasn't much else to say about this. This is good fodder for, like, give me an average value of something, do an operator. We didn't do too much with this. It kind of just gave me some wave functions to do some other types of problems with. So, and it was related to, it's related to chemical bonds. That's useful. And sorry, I just drew a hideous mess. And then, of course, what we did was, once I got into this, then we started doing multi-dimensional for real. And that's where, so like, even I'm kind of having, as much as I don't really like quantum mechanics, I kind of have fun with this until this, no, I hate this. Rigid rotor. Okay, now I'm in hate land. I hate rotational quantum mechanics. Hate it. And unfortunately, everything from here on out is basically rotational quantum mechanics. The hydrogen atom is mostly composed of rotational wave functions. The radial part's rather simple, comparably. Notice I didn't even say too much about them. Well, they're 3D spherical harmonics anyway, 3D rigid rotor. Let me talk about 2D rigid rotor. Okay, so here I drew it there, but let me draw it again because. So the damn thing is in a plane. It's in an XY plane. Don't forget though that you represent it with a angular momentum, and angular momentum is the axle of the wheel. That's just, you can remember that. And okay. So the other part was, I told you as much as I should have spent a little bit more time on kinetics. I don't feel too bad because I actually, the reason I didn't have enough time was because I actually spend more time than I'm supposed to. Like I tell you, I try to do things traditionally. This is where I go off the rails. I am probably the only instructor in America who shows you how to turn this SOB into, oh God, I forgot what it is. 1 over R squared. Remember that homework on number 7? That I told you was a real nightmare? I have the video where I watch it through it, but anyway. So I'm probably the only person who actually makes students learn this conversion. And of course, 3D is over my head. No, it's not over my head. It's just I don't want to spend 5 days doing it by myself, let alone make you do that. That doesn't make sense. So again, the reason that this gets really less fun for me, and probably for you too, is that you really get into a bloody, awful morass of just thetas and d's and product rules, and it's just an algebraic nightmare. Now you can do algebra, and you could since middle school, so it was tractable. But anyway, so you remember this, and okay. So once you get the kinetic energy operator in the correct spherical coordinates, of course R was fixed, and that's why there's no radial derivatives. And also we talked about how the wave functions. I don't know how well this went over. Oh, wrong board. Wrong board, that's burned me before. You notice that I'm not actually teaching this in the order that I went. And I'm doing that because, for one, now that you know more, I should be able to get away with that. Number two, I'm also doing that for the sake of variety, so that maybe if you see things two different ways, it'll stick a little bit better. Anyway, so because you might recall that what I actually did, and by the way, I've practiced this for hours, trying to draw that sheet of paper. Some of you got kind of a little stuck on this, I'm a little worried about that. So you know that what I did was I took particle in a box wave functions and I put them on a piece of paper, and then I tried to put it together, and I showed you that this guy is going to be okay because it's smooth and continuous. They were all continuous, but like this one, this was like the ground state, and that was like the first excited state particle in the box, and when I fold it over, some are okay and some are not. That allowed us to figure out what the wave functions were. They were e to the I m phi, and we have a boundary condition. This is the boundary condition. That's really what I'm trying to get across, is that the boundary condition was, I have to draw it so it's perfect. The boundary condition is that it has to bite its own tail. And the way to do that, we went over mathematically how to prove that the wave function at an angle of 0 is equal to the same wave function at an angle of 2 pi gives us this. Or you can look at this piece of paper and derive the same thing. So anyway, just saying there's multiple ways to do that. You can either look at a piece of paper or do a mathematical derivation. Both give you the same conclusion about the wave functions look like. And I actually began with this. But regardless, now let's go back to looking at the actual Hamiltonian. And also recall that at this point I had to start writing mass out because m is now a quantum number, which is just a gift that keeps on giving. I tried to be as careful as possible with that, but I can tell you one reason is that I had a class where I wasn't careful about delineating mass m from m, the quantum number for 2D rigid rotor, and it got disastrous, and so I got burned on that. And God, where am I at? Yes, that's the energy of the deal. The energies were what? They were, oh yeah. So what was cool was, up until now, you kept seeing energies were always h bar squared, something squared. In this case, they were m squared over 2m. In this case, it was 2I, where mass, not 2, just the mass times r squared is the moment of inertia. Physics, mechanics, you've had that before. And what else do I want to say? Oh, we also had, oh God, I'm not using the board too well, so I'm still talking about 2D rigid rotor. I want to show you one last thing. We had angular momentum. I didn't derive this, and sometimes if I have the time, I actually derive the angular momentum operator, JZ. I should be putting hats on these, and you notice I always mess that up. I think I warned you that. So this is the angular momentum operator, and I know what I like about this is that it looks just like the linear momentum operator, h bar over I dvx. Instead, it's the derivative of the angle, and I just want to warn you that, cool, it looks the same, but that's just kind of an accident. The derivation of this, starting with R, remember this is really R cross P. When you do this and you do all that like homework 7 derivation, it's like 7, 8 steps to get to this, so it's not really trivial, right? You just replace the x with an angle with the phi, but it does come out that way. And then we apply that to the wave function, and you get h bar m, just like you get h bar k for the free wave, you get h bar m. So as I mentioned, the 2D rigid rotor is really similar to a free wave, just a free wave in a track. You know, still not terrible. Here you go, whatever. Also remember that on your last homework I had you do this. What a lot of you messed up was that you forgot that when it came to average value of the difference dipole operator, you forgot to make the final state different than the initial state. So this proved that the 2D rigid rotor absorbs light. That's what you're looking at for light. I've talked about that before. So anyway, so with this guy, remember on your homework, you can show that the thing absorbs light. Recall that if I ask something like this, the final state has to be different than the initial state. That's why it's a difference dipole. And that's because you have to account for the energy, right? These are eigenvalues of the Hamiltonian. If they're the same, then there's no energy difference. And so it didn't absorb the energy of the photon. What? That doesn't make sense. So anyway. Now, the reason that was important was that was why the wave function cannot be e to the im phi plus e to the minus im phi. So what I'm trying to do here is emphasize the idea of what uncertainty does in quantum mechanics. In the free wave, this was okay because I didn't know whether something was moving right or left. But in the rigid rotor, it is not okay. It is not okay because if I'm told that if the great turkey in the sky tells me I have a 2D rigid rotor, I'm allowed to shine light. I'm allowed to shine light on it. I'm tired. I'm allowed to shine light on it. The transition is not zero, and I can distinguish whether it's moving right or left. So again, this is never okay, because I can always take the 2D rigid rotor and shine light on it and figure out whether it's moving left or right. You cannot do that with the free wave. If you do this calculation with the free wave, you actually get zero. You get zero. I just wanted to point that out. So, okay, now with this done, we took the journey to Mordor, which was the 3D rigid rotor, and then the hydrogen atom. And so I just want to go over, so now we're at test 3, but I want to review a couple of things and just remind you. The 3D rigid rotor did kind of spill between test 2 and test 3, so I just got a little bit more to talk about there. And I haven't dropped too many hints about the test, I know, but that's because a lot of the test is very general. So, what is quantum mechanics? What's the role of probability in quantum mechanics? That kind of stuff. Okay, so, of course, what we do is when it came to free wave, I always did just X and Y, because just Z is more of the same. When it came to the 3D rigid rotor, and of course the hydrogen atom, that's really not true. Of course, I didn't have you turn this to spherical coordinates because, again, that's the most hideous thing that's ever possible. I really don't know of too many other things that are more complicated than this. So I remembered that we also did a little bit with, you can turn the radial. You can turn operators into other operators by applying dummy wave functions. I had that on one of your tests. I didn't put that on this one. But what I do have is I took one of the model systems, one of the quantum model systems that we did not cover, and I have you do a radial operator on it. Not this one, but one of the related ones, and that's the extra credit question. So. And again, I think you'll all nail that. You seem to have done pretty well figuring out how to deal with eigenvalue equations. Now, again, I don't even have a handout on this on how to turn the 3D into spherical, and that's because it's even. Again, I know I can do it. I know I can spend the 5 days of algebra and get it. I just don't want to.
And so I do not have a handout to do this. In fact, I'm not even sure where I'm sure if I Google it, I can find some Schwab has at some point worked all this out. I mean, it's kind of a miracle. I mean, think about this, what's kind of funky about this, I mean, think about these waves. They go on and on and on and on. These waves can go on forever. So how the heck do you model something that goes on forever with radial that's like stuck in a sphere, right? It's kind of miraculous that it can be done at all, and that it's not like some kind of infinite series, which I would kind of think you would get because, again, waves go on for infinity. Anyway, so it is what it is. I can't really say I understand it. Okay, separability. Separability. That is the thing that I harped on quite a bit in this class. So once we had this, okay, I'm still talking about 2D rigid rotor. I don't think I'll talk about hydrogen atoms. But remember that separability is the mathematical process by which you solve this thing. Now, of course, this is equal to E, so we often expressed it like this. And again, this is the form that a mathematician would prefer to see so that they could solve this. And what you wanted to be able to see here is that you've got a term with R's, a term with thetas, and a term with phis in it. So excuse my crude expression here, but I'm praying you know what I mean. Right, so a bunch of stuff with R's, a bunch of stuff with thetas, a bunch of stuff with phis. And when that happens, the wave function is the product of separate wave functions that each one is solved on its own in these become sub-Schrödinger equations. Each one is solvable on its own. You do so and multiply the results. Now I know this is kind of mired in pure mathematics. And I don't want to blow your head off from that stuff, but it is kind of important to understanding this. I have no idea if you'll run into this in your professional lives, but anyway. Okay, when I do that on this SOB, when it comes to the 3D rigid rotor, okay, I got all my phis together. Remember, this doesn't quite work out for the hydrogen atom due to the radial spilling over into the theta part. And okay, so here's a blob with phi in it, and again, I'm not doing the hydrogen atom, so the R's are gone. So I may ask you just describe. I wouldn't have you write all this out, but maybe have you describe it, something like that. Again, the test came out very descriptive this year, and okay, so there you go. This guy. We assumed that the 2D rigid rotor was still part of the solution. I haven't put out the energy yet, so that means that the rest of this, now I have to add the energy. There's my masses and whatnot. And remember, this guy comes about from simplification. Okay, that means that the rest of the mess is equal to plus m squared. Okay, so this sub-Schrödinger equation is already solved. We assume that we did it in the 2D rigid rotor. This thing equal to plus m squared, as I mentioned a million times so you're sick of it. Daniel Bernoulli in 1783 or something, swear to God, just said, hey, I feel like solving this. No idea why, but it was done. The answer was spherical harmonics. We've gone over those ad nauseum questions.
You're going to ask us to describe this equation. Can you give us an example for this on how you describe it?
Well, no, what I ask is that for you to take the sine and divide it by no, I'm just kidding. Well, then, even it's class a year. You know I'm not going to throw anything that's 10 miles long at you. So if I have you describe it, I mean, I want you to hit this level, right? That's the final. I want you all to pass. I mean, it makes me look bad if you're not doing well. So, I mean, if you're not showing up or something. So yeah, I'm not going to throw anything 10 miles long at you. And even if I did, because I haven't quite written that last question yet, I'm gonna make sure you have all the tools you need to do it. So you've been around long enough, you can trust me on that. Okay, so again, Bernoulli solved this, I think it was Bernoulli in 1780, somewhere along those lines. And cool. Not that it meant anything to him, this was just a math problem for the hell of it, which is, I know in math class they still do that, right? They just, here's how to integrate with that method that you were told works all the time, but I'm telling you now, actually only works some of the time, most of the time, but not all the time. You have to take more math classes to see the reality. So we had the wave functions, I'm not gonna write those down. P, D, blah, blah, blah. And this is where, what's also kind of interesting about this is that the energies no longer quite look like, it's no longer h bar squared k squared over 2m. It's no longer h bar squared m squared over 2y. It always looked like that. All of a sudden, they start looking, it's almost like that, right? If there wasn't that plus 1 there, it'd be h bar squared l squared. Almost, it's almost h bar squared l squared, but it's not quite. And of course, when we did the hydrogen atom, it got even a little harder. Oh, other salient, okay, like what could I ask you, I guess? Notice how energy also funneled down into one of the sub-Schrodinger equations. That just happens. I don't know that there's any special meaning about that. Besides, even though the energy funnels down to this one, this guy still has an influence on what happens because, look, it's still equal to m squared. So I don't know if I'm really saying that correctly. Not because I've screwed up, it's just I really don't know whether it's fair to say that E is only solved here because, I mean, this guy is still communicating to it. And so anyway, I thought that was kind of fascinating. And we also talked about, and I didn't put this on the test, but we talked about how in 3 dimensions the guy is spinning like this, but we have an uncertainty principle. That means that the axis, the J vector, is actually rotating about. Of course, this has a projection of m of 0, and if we have a tilt to that, because we're talking about a P state or a D state, you get little cones, and now my drawings look like crap. Well, anyway, sorry, I shouldn't have continued on with that. And after that we had H atom. And actually my notes are done now, so when I send them to you, look out for that. But the unnormalized, I don't quite remember what the normalization constants are, but it's basically R over A naught. A naught's, of course, a Bohr. This is the radial. The radial ends up being the most important because, again, the energy funnels into that. And that's for a 1s state. I had you draw S versus P. Oh, the one thing that you guys really messed this one up. And I didn't put this on the final as a result, but it kind of threw me off a bit. I had you do, which one has more rotational energy? This one? Now let's see, yeah, now we're going to see who actually looked at the answer key. This one or this one? Which one has greater rotational energy? First one. No. God, you people, please. Okay, help yourself. Look at the answer keys because you probably got a lot wrong. This is an S state. Right? It's an S state. This is either a P or a D state. Can't really tell, right? That was the point of another question on the exam. And that's because you've got a 0, 0. And so only P's and D's do that. That means they have rotational energy. This one doesn't, because it's an S state. The question.
What's an S state?
For you, that's when the cat throws up. And the answer to number 3 is 5. And, okay, I shouldn't tell you this, but one time I hid the answer to a question in one of the extra credits. Like I said, number 3 is 5 or something. Maybe I'll do that. Now, I haven't done it yet, but now I'm thinking about doing it. I'll let you know. I'll let you know on Wednesday. But I may not be here because I may have jury. Why don't we end just a little early? Again, hydrogen atom and kinetics came next, but I just went over that, so you should be okay. 2 kinetic questions. There you go. All right, everyone.